We'll now go on to our third speaker, Professor Olsen. You've heard the Olsen formula being mentioned. Thomas Olsen is a professor in Denmark, created the Olsen formula, and I think that there's no better person really to take us through it and explain why it's such a good formula. So Thomas, over to you.
So these are my financial disclosures. I have been working in this field for some years and I have some financial interest as well. I want to take you through these steps, just a short history of IOL power calculation. I know you had a lot of information from Doug already, but no harm done to view it once again. You know, we have more than 50 years of IOL power calculation formulas out there. And you know that it all started with theoretic formulas based on optical principles, but soon after that we had the regression formulas because they seemed to be better. And then we had improved thin lens formulas, and now we have improved biometry and we have better ELP predictions, but we're still not finished whether we should choose optical based formulas or we should choose regression or statistical formulas. So that's interesting to see. And you have to realize that many formulas, they use a kind of black box mechanism to find the secrets of their formula. That also goes for optical formulas. You need to find the ELP, and many thin lens formulas do it that way, that they back calculate the ELP to get the ELP as a function of a lot of predictors. But if you go to more higher sophisticated statistical methods, you can find the same procedure in artificial intelligence as well. So the battle goes on. There's an optical and there's a statistical approach. We also have the geography. And I don't think that we beat each other, but it's nice to have some competition. So I'll take you out of the black box and we'll discuss some of the fundamentals. And what are the fundamentals? Well, if you look at the formula of a thin lens formula, it's very simple actually. And it's based on the divergence principle, that you have the divergence at the back of the lens and your divergence in front of the lens. And by subtraction, you get the emmetropic IOL power. That's it. But there are a number of questions. What is the true axial length? That was the problem in the old days when we did the ultrasound. I think it's less a problem today because optical biometry is so accurate. But we're still left with the question, what is the true corneal power? And neither the cornea nor the IOL are thin lenses, so the optics will break down if we apply more sophisticated thick lens theory. And finally, how can we predict the ELP? And that's a very good question. The corneal power, what is it actually? Well, you know, if you take a K reading, what are you doing? You're not measuring the power, you're actually measuring the radius. And most keratometers, they are calibrated with this index of calibration. So if you take the anterior surface and you think the cornea is a thin lens, you get this power from the index of refraction. Actually, it means a 10 millimeter radius is the same as 37.5 diopters. But if you look at the thick lens situation of the cornea, you have the front power, you have the back power, and if you combine these, you get another number for the index of refraction. This was actually my entry into this world. As a student, I published this work because we had a lower index of refraction that might reflect reality better. But nowadays we can do more than just theory. We have ray tracing technology. And as you know, many newer techniques can give you a lot of 3D data, elevation map, matrices, and all that. This is an example of the Scheinflug, the Pentacam machine that will export these kind of data. You have the height elevation there in all of the areas. This is the elevation data in microns. So you can actually shape the entire shape of the cornea, both on the front and also on the back surface of the cornea. And why not do a ray tracing of this surface? There are technologies out there that can be used for this job. And this is an example of the real Pentagram data of patients I have imported into the CMAX engineering software. And here you have the front surface of the cornea. This is the back surface, and all the triangles that we combine to make a physical shape for which we can do exact ray tracing. And if we do that, we can also put in a pupil, and then we can analyze where is the focus. What is the focus? Well, a focus is the point where you have the highest point spread function or the least blur. So if you do that and go for the distance giving the least blur, you have actually the power of that cornea. And we have done that in a number of patients here. This is a ray traced cornea power. And here you have the other metrics. The black dots, that's a K rating if you use the wrong index, I told you. And also the total corneal refractive power, which is given to you by the Pentagram, is in the middle. And actually the total corneal refractive power is claimed to be ray traced based, and it actually fits very well to our data from exact ray tracing on the cornea. So my point is actually, before we put any formula together, we must make sure the cornea power is right. Otherwise, we don't have the physical reality. So the most critical unknown is actually the IOL position. I prefer to talk about the IOL position because the ELP is such a virtual distance, it's not always reflecting the physical distance in the eye. But if we try to focus on the real position, first of all, that's just the ELP of a Finland formula you're seeing here, and you have the old formula out there. And that's the distance from the corneal surface to the effective lens plane. There are a number of formulas out there, and they have all their own method of predicting the ELP. You can see also the time scale is going down here. We started with the K rating by the Fjorov formula in 1967. The Binkos were using the action length, that's the only ELP predictor. And then we have the SRKT combining the action length and the K rating. Actually, they copied some of the Fjorov approach. And you go down the list, and if we go down to the the formula doesn't use the K for the ELP prediction. And that's very important if you talk about the post-LASIK cases, for instance. And of course, as Doc always mentioned, the Holiday 2 uses additional parameters like the refraction, white to white, gender, age, and many others maybe. My own proposal is to use another approach. I've always liked to use the physical distances and not just talk about the virtual distances. And this is how we did it. And it all came because the LensStar came out. And you know, the LensStar can measure an A scan of the eye, just like the old ultrasound technique. But also after surgery, you can actually measure where is the IOL located in the eye. So this is very important. And we have been doing that for many years. And here you see a series of 1,622 cases where I have the IOL position. That's the center of the IOL here. We plot it against the actual length so you can see the dependence. The blue dots, that's the anterior capsule, pre-op, or the ACD. And the green dots, that's the posterior capsule of the lens. So the distance from this line to this line, that's actually lens thickness. As you can see, the IOL center is located within the lens. No wonder. I put it there when I did the surgery. But the trick is there's a mathematical relationship. And this is what I call the seek constant. The seek constant is very simple because it depends only on the ACD, pre-op, and the lens thickness. And here you can see the formula. By a fraction of the lens thickness, we add to the anterior chamber depth, then we get the center of the IOL after surgery. It's very important to realize that this constant is not depending on the K reading nor the action length, and it's going to play an important role when you go to the post-LASIK cases of very odd corneas. And you can also confirm the principle if you do modern OCT technique. This is a pre-op scan of a patient that has a post-op scan like that. That is the IOL situated there. And if you superimpose both images, you can see there's the IOL. And actually, if you measure from here to here, you will find it's about 40% of the crystalline lens thickness. And that's a very typical number for the C constant. So going back to the sources of error, well, the situation has changed since we got the optical biometry. Then the actual length is minimizing in its size. So we don't have very high error from the actual length measurements, but the ELP or the IOL position is counting much more in a relative sense. Maybe we should concentrate more on the K rating, like Adi was saying. This is maybe the new frontier. But the most important source of error is, no doubt, the lens position. What about the clinical results? Well, there have been some papers out there comparing the Olsen formula to some of the other formulas. This is a work by Koch and Cook from 2016, comparing up to 9 lens power calculations. And the Olsen formula came out quite good on the top, together with the Barrett formula. And also, as Doc mentions, we have a huge series from the Kaiser Permanente company. And this is published in Ophthalmology 2018. They had more than 18,000 cases, all done with the LensStar biometer. And in both, this was the original paper, and then we had an update because newer formulas were coming. And as you can see, the best formulas in the update publication, that was the Kane, that's a new formula from Australia, and the Olsen and the Barrett, all achieving more than 80% within half a diopter in a routine cataract series, I have to note. So I had the opportunity to analyze the material from Ron Mellers, and here you can see my comparison of the formulas. There's no doubt that the old thin lens formulas are not doing as good as we want it to be today. And in this case, I was down to 0.3 in the mean absolute error. That's about 0.4 something standard deviation. And also, if we count the number of cases within a half a diopter, you can see we are below 75 with some of the old formulas. And then we go up, the Hill RPF is 77 or something like that. The Barrett and the Olsen were about 80%. If we plot the error along the actual length, you can see that we are actually doing quite good in the long eyes. So we are out of those old days where we had high errors in the long eyes. Actually, the accuracy in this material was the highest for the very long eye. We still have problems in the short eyes, and it's got to be that way because the short eyes have smaller dimensions and every error counts more. So what about the future? This is very interesting. And I don't know about it, but one thing we could do is try extrapolating. And I do have some experience. I've been in this field for more than 30 years. And I looked through all the publications that I have made. And to get the error in each publication, here you can see the error as a standard deviation or the mean absolute error. It has dropped quite significantly when we started back in the 80s and 90s. And the reason why we are having better accuracy today is, of course, we have the optical biometry in around 2000. And 10 years later, we got the LensStar biometry that allowed us to do a more elaborate analysis of the ELP prediction. Another way of putting it is to count the number of cases within a half diopter. And Doc, as you can see here, now in my own series, we are better than 90% within a half a diopter. So in 5 years, we have more than 100%. How about that? So in conclusion, I would like to say that my approach has always been to divide and conquer the unknowns. We should pay attention to the measurements and the physical reality. And this is how we can get methods to predict the IOL position. I really believe it is possible to predict the physical position. And then we have, the rest is just optics, if you allow me to say that. So if we have these methods, we can do accurate and unbiased calculations, and we don't need any magic. And this is my point. I thank you so much.
Thomas, thank you very much. That was just, again, just a tour de force, and it summarized so well everything that the other speakers have spoken about. And I was just thinking, it's amazing. It's not often I've sat to a lot of lectures to hear someone who quotes their own research that they published 35 years ago, who's still relevant to the same subject is amazing. And it's a real testament to you.